Well, hey, I'm back. I let this guy sit overnight, and let's see if it's discharged. Yep. Yep, discharge enough. 17 volts, I think I can deal. Okay. So first things first, I want to take a little more hardware apart here. First off, we have this little chip right here, and it is an AVS1AC. AVS1AC, AVS, and I bet it's a automatic voltage switcher from the location. Yep, it is an automatic voltage switch. So what this guy does is it takes care of the automatic switching from 12 volts or 110 volts to 220 volts when you plug in the line cord. So that's the reason why there's no little switch. Originally I thought this jumper was for doing it, and after looking around, all this jumper really does is it ties frame ground through the various screws to the ground pin in the power cord. Why the heck they did it that way, I can't tell you. So, you know, it splits off ground on the cord, this MOV, and these two MOVs. So, maybe someplace where they sold these, that was a requirement. I really don't know. So, anywho, as you can see, this chip requires a second three-legged device, an external triac, to make this working. And what it does is, when the voltage coming in is 220, it disconnects the center leg, so you don't get this voltage doubler effect. And when it's 110, it connects the center leg, so you do get the voltage doubler. So you always get about 300 and some volts out the output side of this thing. The fact that I was getting 300 volts across these two caps, or 330, tells me it's either working or at the very least it's shorted, in which case it's working good enough for me. Right there I have an AVS 10CB. 12CB. They didn't run that all the way. Oh, they did. So these two act as a pair, and in most power supplies you'd see sort of all the input stuff grouped together, then you're switching, then a big isolation gap. In fact, do I have one right here? Yes, I do. So in this doohickey, where the power came in right here, then you had your switching and your big filter caps, and then in here was your SMP switching. And then if you notice, there's this great big huge gap going down the center, where there's nothing crossing between those two halves other than the transformers, the opto-isolators, and for some reason it's either a cap or a mob. Hard to say. The reason they do this is for what do they call it? Electrical creepage, I think is the term. Basically, it's so that as dust and dirt and dendrites grow on the board, there's no chance of this flashing over to the low voltage side. Now, if you notice on this guy, there's absolutely none of that. They got low voltage, high voltage, medium voltage, everything just sort of crisscrossing each other. So apparently in '94, UL didn't have those rules in place, which is too bad. In other words, this thing's a little scary. If something goes south, it could go bad in a hurry. But anywho, so I bet power comes in here, fuse, AC cap, hits this transformer, which I'm willing to bet is just an isolation transformer. Or no, sorry, common mode choke. Yeah, power comes in there and comes out right there and there. Control signal for the FET, or not FET, triac, and then that all feeds over into this stuff. So this, so far, that I've traced out is that exact circuit, like copy and paste, but more or less it's an exact copy of that. So that's this mess right here. So infuse, common mode choke, rectify. This is all surge protection stuff, more or less. Switcher to automatically detect 110 versus 220, which then this all feeds over into this guy, LT1105, which must be the power supply control chip. And there it is. So they call this an offline switching regulator. And it's all super hot. Wonder bar. BUK. Where is the pin now? Pin 8 is the one that goes to the regulator switch. So what this thing does is, based on the feedback from this coil here, I don't know if it PWMs or how exactly it sets up its high-speed switching, but you know, it changes either the pulse width or duration to this coil. So it's regulating on the hot side of the transformer, and then you know the secondary side is just fixed. So as you load the secondary, it drags down the primary, which causes this to go down, which causes it to pump more energy in it. The main thing that does all the switching is this guy right here. So let's see if I can find him off. This is actually a pretty decent data sheet. A lot of these old data sheets were a lot better than their modern counterparts, because there was no internet. Well, there was the internet, but not everyone had it, so they'd send out great big huge data books to designers to pick their parts from. And if all their questions weren't answered in them, they'd either pass the part over or spend a lot of time on the phone with an engineer at the company that produced it. This guy has two legs, so I'm pretty sure he's some sort of diode. And his number is D7. These two have Qs, so those are probably the switches. This has a U by it. It's a regulator. Low dropout regulator. What voltage though? CT-5. Something that explains the differences, but they don't in this case. Important bit here is it's positive, adjustable, and fixed. I'm betting that -5 means that's a 5-volt regulator. In, out, adjust. In. Ooh. Oh, yeah. So ground is hooked to this tray switch, since it's tied to the frame. Pretty sure is ground. outputs in the middle and ins on the other side. In heads underneath those big caps there, so I can't trace it easily. And so does out. Guessing it's going right there. Come on. Right up to there. Is that a relay or a cap? That's a cap. Yep, that's +5 coming out of there. Okay, so I got that figured out. 5-volt diode. Resistor network. So I'm guessing Q1 here is the switching device. And he is an IRF BE30. IRF BE30. MOSFET. Yep. Gate drain source. So this chunk here in this is the input switching. This here is the high voltage switching into the transformer. And I bet the secondary out of the transformer goes to this, gets rectified, filtered a little bit, fed out to this goop, and also converted to 5 volts. So at least one of the outputs of this thing is greater than 5 volts. On that topic, there's a lot of windings. Yeah, he's good. What I was doing there was just using the diode function of my meter has enough charge on it that it'll charge up the gate on these FETs and turn them on. And then when you reverse the probes and touch it again, it turns back off. So the body diode and everything's good on this guy. Which is, you know, looking more and more like there's something else wrong. This switcher chip right here is obsolete. I can't get them. So it's sort of, you know, real bad news if that's what's wrong. Let's pop the diode right next to it. I don't know what the output voltage of this thing is. I wish I did, because I could pump it in right here at this diode, which would then power up this external connector, the LED, and then it feeds down into all this logic. And I seem to remember, no, we didn't trace that one back yet. So I'm not exactly sure what voltage that is, but that could have been a really good spot to wire in a new power supply if the drivers are good. Quite frankly, this power supply is a little scary because it doesn't have the isolation. Yep, that diode's good. So it's looking more and more like something in Kya is bad. Let's see if I get lucky and get this transformer off. Now the datasheet has an example for a high current 5-volt supply with optional 12-volt windings with recommended transformer and transformer, I guess you'd call them setting or specifications. So I'm hoping, based on that, I can ring out this transformer and see what the various windings ratios are, and then between that and the data sheet figure out what my voltages are. You know, anything that hits a regulator like the 5-volt reg, it's like doesn't really matter what comes in as long as it doesn't blow up the reg. And there's a negative voltage regulator in the opposite corner of this board, which tells me there is at least one negative supply coming off of this. And again, if it doesn't go anywhere other than that regulator, I can just hook up whatever I want, or just disconnect it completely if I'm not going to use it. One transformer. Okay, let's quick see which windings hook to what. So I'm guessing these two windings hook together because they're weird. Yep. These two windings based on where they're at. Ooh. Oh, it's off by a pin. Yep. These two little windings here. Yep. These two. Yep. And these two. Yep. Okay. So it looks like we have 3 secondaries. Primary in a sense. I wonder if these red, now that this is off, it's much easier to trace this stuff. So both this and this are positive supplies, and this is the negative supply. What the heck that negative supply is actually used for, I'm not so sure. Tell me the fan's running off of negative voltage, in which case this is minus 12. So I think this is a 12 volt fan. 12 volts. Trace something wrong. Let's mark that while I'm thinking about it. Oh, now that we know what that is, what just dawned on me is this is a 12 volt fan, so we know the power at this connector is 12 volts, and we can follow that back. There's not any, Semiconductors in the way. Oh. We're running the fan off the minus 12 volt power supply. Well, I guess that's something. Let's go. Let's grab that fan and just double check that, because that's way too funny. Good news is, I now know what it is. It's just really, really funny that they decided to put the fan that's totally it. They put the fan on the minus domain, probably just because they didn't have a lot of load on it, and it took a little bit of load off the positive domain. It's still really frickin' funny. You know, in modern computers today, you don't even have negative domains coming out of the power supplies anymore. Now that I know what one winding is, I can go and throw kilohertz-ish sine wave from my frequency generator into this coil, and then measure these coils and just look at the ratio. So if this one's twice the voltage of what I'm putting in, we know this is 12, that's 24. If this are 1 to 1, then we know they're both 12, and that'll get me my other two domains. The current thought going through my head is to just sort of whack the power supply completely off this board, and then just go and get a more modern supply to supply the 12 and whatever other voltages I need, and just save the stepper drivers. That said, you can replace this whole thing with one of those little stepper driver polo modules. So it's just like, man, I'm going through a lot of work for very little payback. Let's see where else minus 12 goes, because I might not need it. So that looks like it goes up into the control board. So this portion of the logic probably doesn't need this. I'm going to make the silly assumption that that is not needed. Okay, I just saw something important that may make me change my mind and just dump the idea of getting this board working. If you notice right here, this whole chunk of traces, they just sort of head down here. They hit the LEDs, but more importantly, they also hit the pins on the H drivers. Or at least, well, maybe not. Those might just all be status LEDs. And if they are, then I'm more okay. My hope is somewhere in this header is just the step and direction fed into these. More and more I'm thinking it might not be. And I think I might call it quits. I want to work on this more, but I'm so tired. Okay, let's look up one of these real quick and see where the control comes from. Okay, these little guys are 2K resistors. So 2K, 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 2K. They're not bussed together. Okay, that might kill this exercise in futility right there. So what I just found out is those H bridges go straight to this board. And as you can see, this board has 4 limit switches coming in and 4 outputs, which means 8 wires, 1 step, 1 direction to get it back to something I can use with EMC2. So I need 12 pins total there. So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which would only leave 2 pins, which right there they are, and they're hooked together because they're either power or ground. Also, the wiring from this connector goes straight into this connector here and up into this board. So I'm pretty sure this is the step generator. I could get this thing working again with a new power supply, I think, if nothing else is bad. That's a pretty big if at this point. I'm thinking just going and buying some cheap Pulu, whatever called drivers off of eBay is the better way to go. I'm gonna go double check, find myself my mirror. Yeah, let's do that now. Let's go find a mirror and check the current rating on that motor that's up and underneath. Those H bridges on that guy are only rated to 4 amps, a little over maybe. So that right there is a good starting, is probably what they're actually were being driven to. Since I'm going through the effort of rebuilding this thing anyways, I might as well do it right and get whatever the maximum current this stepper could draw for my stepper drivers, because I don't think it's so unreasonable that it's going to like cost huge amounts of money. So 2.58 amps or volts max, 4 amps DC. Model. Okay, so it's a 1.8 degree. .58 amps unipolar, or 2.5 volts unipolar, 40C, date code, 4 amps. Okay, so it's only a 4 amp, 4.0. 4.0. So this is a 4 amp stepper, and I'm pretty sure 2.2 amp, and that one was 0.6. So I only need 4 amps of stepping power max on my biggest channel. So with that, I think I'm totally going to put this guy back together quick, just so I don't have all these parts laying around. And that way, in case someone does need parts off of it, I have it available. And totally punt this, and potentially this. I may use it to start with until I can find a touch screen to replace it. But we'll see. Something interesting I just noticed is this has been cut. At one point in time, I bet you this was one continuous U. To service it, you had to take the whole thing off, and someone decided to make the lid removable. Kind of interesting. So from that and the touch-up I saw earlier, I'm having a sneaking suspicion these things blew up frequently and needed repair. So my guess is that switching regulator is dead. And probably replacing that would have brought it back to life, but meh. I'm not going to use it. I'm not going to spend any more time on it. As you saw briefly in there, I beeped out the sensor. Main things I wanted to know was the bias or current limiting resistor for the LED, and which pin was the output, power, ground, output, that sort of stuff. So I got that all written down. That's ready to roll. And I think with that, I'm going to call it a night, because I'm really tired now. And like a noob, I got heatsink compound all over my nice black shirt. It looks wonderful. What else we gotta do? I'm going to hold on to all this for now. I may reuse the panel because it's pretty straightforward. It's a 4x40 character LCD. Those look like pretty common driver chips. At least I've seen these used on before and successfully gotten them to work. A couple of standard logic gates, 74 series, I can figure them out. Power, ground, whatever, beep it until I find the right ones. It's too bad this faceplate is all crapped out. Maybe I can find someplace out there where I can just print a new one. I think my plan is going to be is mount a Raspberry Pi in here and have it drive the works. I might replace this whole thing with just a touch screen so I can
do it however I want. Else I might see if someone out there in the billions of services prints, what is this? Yeah, it's like a plastic sticker. Can print me up a new faceplate with contact adhesive on the back. From possibly a scan, maybe. I don't know. Brain's fried, going to bed. Thanks for watching.